So basically, in the last lecture, we started talking about this layer with specifically the APIs that frameworks such as TensorFlow will provide. We also mainly discussed this conceptual and very important and interestingly common across all of these machine learning frameworks like PyTorch, TensorFlow, is the key concept of computation graph. And we, at least I hope that you got the idea why this computation graphs are important for machine learning, and what are the opportunities at least they provide. Specifically, we went to some detail, some of also examples, for example, in terms of optimization, for mainly about through backpropagation, providing this gradient of the loss with respect to all parameters. This was what we wanted to get, hopefully efficiently, because we needed, once we have this, we can go ahead and change the parameters of the network or the model iteratively, right? This was the key idea, or the key basically procedure behind all of these optimization procedures that we learned, and you got the idea, right? They look somehow similar. Some details are different, for example, the implementation detail, but the key idea was basically we needed to calculate this guy in order to update the parameters through these update rules that you know about it. Both for different models like logistic regression, neural networks, other kind of models, they're similar. So we have optimization. During this optimization, we need this guy, and computation graph provide this very efficiently for us. So that was, we mainly discussed, and we learned why we need this upper layer part of this machine learning stack. Okay, now we move slowly down. So today my goal is to really give you some overview and like some intuition why these the other layers, like this system level, also this hardware level, are important. But we will go into details, like the way how we treat this computation graph with some examples in the following lectures. But today the key idea is to basically get some overview, high level intuition behind this system stack, and then we move toward the detail afterwards. So before we continue, do you have any question you want to discuss? Again, as always, could be about anything, could be about this, or could be about your project, whatever.
I actually had a question, but it's mostly for the class, just because I've been wondering this, is just like, how many people have actually figured out how to get the research project that we're doing, the dependencies resolved for it? Because I know a couple of us have been talking about it and having issues. I think one person has solved them, but yeah, okay, that's some people are saying in the chat, because I'm trying to figure out, like, has anyone actually, other than maybe like one person, figured it out?
Okay, that's interesting. Yeah, my message is that try, but Ying will meet with you guys over the weekend, right? Saturday. And for those who cannot join, at least you can watch. So to figure this out. But hopefully a few of you already basically got this, all of the dependency installed, and you can start. Yeah, absolutely. All meetings will be recorded. and will be available to you guys. Yeah, definitely Ying can help you guys, but you need to really spend time. I know that you did, but this is the way how it works typically. You know, this is one of the challenges. You will get familiar, but you will learn throughout these struggles, right? So next time, this stuff would be a lot easier for you. Right. And maybe some of you may want to create a Docker image or something that that facilitate this or automate this, right? So we can write Docker script to automatically install all dependencies and prepare an environment so you can start doing your experiment easily. Maybe talk with Ying, you can do it together. Yeah, that makes things a lot easier, I would say. Okay, any other question? Are we good? And yeah, please, like for those who will ask, I would prefer, as I said, to see you guys. So so enable your camera. Okay, so let's and like on Piazza I mentioned this, right? So we have some extra, more possibly interesting kind of task, obviously optional for those who are passionate about doing some research, right? Who think that maybe they are interested, you know, doing research in this direction, because as I mentioned, this adversarial machine learning is a really hot topic, and there we have several ideas for you guys to work on, and like if for some of you, if you're interested in doing like graduate level kind of research, yeah, there are opportunities, and contact me or Ying to discuss detail. I put some detail on GitHub, but we can also, there are much more detail to give you an idea, at least how it looks like. And another update is that I will send you the latest and much more polished version of the paper, Athena paper, with much more results and more interesting discussion. So I would encourage you guys to read it, definitely. And you will learn more, hopefully, and give you an idea of what kind of discussion you need to put into your report and what kind of maybe plot you want to do. And all of the scripts for making these plots will be available, so makes your life a lot easier for you. Do you have any question about, like, at least the stuff that I put on GitHub? If you have, maybe if you want to discuss some detail, I'm happy to talk about it. So basically, this idea, I mean, more specifically, we have a couple of ideas, but this one that I mentioned is more about like evaluating this Athena framework with real world kind of scenario. By real world, I mean physical scenario where instead of deploying the defense on computer, right, on a server or something, or on your laptop, whatever, now you deploy it on some real devices, as I mentioned, right? Some devices, small devices like this, right? So this is Google TPU. This is even a smaller Coral device. And the key idea is that, okay, the difference really is that like when you deploy the defense, obviously you can add a lot of weak defenses, a lot of these transformations, basically as much as you want, or as much as you have resources on the server. And in the result, at least in the result we reported in the paper, you see that as we add more weak defenses, defense as a framework becomes like stronger, right? But it obviously comes with a cost, and the cost is like you need to load more. So you need to load these models into the memory, right? And once you move to these smaller devices, obviously you cannot put anything here, right? So that then you need to think about the trade-off space. And within these environments, the other difference is that like it's not the case that you feed some digital input, like some digital images, right? So you have this standard benchmark, which has a clean training and test set, like MNIST or C400. So these are clean and clear-cut, like digital images. But like with this, you need to think about like real-world images, real-world objects, right? So for example, you have some object and you point the camera into this, and you need to think of, okay, how I want to, how I could perturb real-world scenario, real-world physical object. There are also work on that, right? You can maybe do this perturbation, synthesize this perturbation on your computer and print this perturbed object, and then point that perturbed object toward the camera and see whether the defense can recognize this, or like the deployed system can recognize this object correctly or not, with and without defense in place, right? So you can, one nice scenario could be that you have one physical object, then you also do the print of the perturbed objects, and then you show these two with and without defense in place, and see how it works. And you do this for multiple objects, and then you report your findings, right? That would be a nice, nice experiment. And also talking about the trade-off space, okay, how many models you were able to deploy, basically what was the size of the ensemble defense that you tried, did you face some of interesting challenges, did you, for example, measure energy consumption, like how was it, right? Some of these ideas which provide, as you can see, different aspects about the real world machine learning system in a real world and interesting environment. This could be really interesting. And as mentioned, we have also some other hardware platform like AWS Deeplands, which is also a nice hardware platform. Specifically, it has camera attached with it. It has the capability to deploy models on the device as well as in cloud, even partially. So you can put some part of the models, and with Athena you can do that, and that would be interesting thing to try, right? Whether you can deploy Athena in multiple places, right? Part of it in cloud and part of it in the device. Obviously, this needs to be designed and think through and see how you could do that, right? It's not trivial. It is possible, definitely. everything is possible, but it requires some creativity. Right. The other idea was also about like hybrid ensemble defense, where you saw in the paper like the ensemble defenses that we tried was mainly homogeneous in a sense that like you have a neural architecture, so you have a specific architecture, you train these weak defenses with the same architecture, right? And you construct the ensemble defense of these homogeneous architectures. One other idea could be, right, maybe some of the weak defenses could be trained on one specific architecture, some other could be another architecture or another type of model, like could be a combination of SVM and neural architectures or anything, right, you can come up with. And several other ideas if you are interested. We can also, we'll provide more information about this as we move, but we can also set up meetings to discuss more details if needed. Okay, so let's discuss about this. So again, we move downward toward this system stack to see how it looks like. And again, specifically about the example, right, we had on the slide, right, about this this particular logistic regression model. We discussed about the difference, right, when you do that in a NumPy with no support from a framework like TensorFlow, and how it looks like in TensorFlow, right, and stuff. But in terms of computational graph, it's very simple, right? So you have some inputs, and again, to talk about this, because it is important.
Sorry, I couldn't hear what you said.
It was okay. So it is important to know about these differences, because again, to give you a high-level perspective, you know that we start constructing this stack by these variables, right? These, for example, in this case, we have A and B, right? So these are the variables, and we have some operations, right? And we construct this computation graph. Like for example, here you have constant, and then you have another operation. This is for this operation, right? So you see the mapping here is straightforward. So for example, corresponding to these 3 lines of code where you use TensorFlow, right? So here you introduced variables, right? You introduce here X, right? You introduce W, and also the corresponding size of the variable. And by the way, to make it more generic, so these nodes could be like anything, right? So in terms of type of this, could be a matrix, right? Could be a vector, could be a scalar, right? Could be even, right, tensor. Could be anything, right? These guys, and like the edges represent these operations, right? For example, these operations, as you see, right? So you have these, and then you have y, which constructed or computed based on these operations, and then softmax, right? So you see the correspondence, and then like for these, so you see that we have this variable, this guy here, specific size again. Now you want to calculate cross entropy, this guy. So you need to start by taking the log here, right? So this was the y. You need to take the log here, and then you need to multiply that with y, right? Y underline, and then take the average, right? In order to calculate the cross entropy. Okay, so the correspondence is really straightforward. And then, in order to calculate the gradient that we discussed, this case it is called W graph, but this is basically the gradient of the whatever we discuss about the gradient of the loss with respect to the weights, right? So here, and this is like by something like framework like TensorFlow, you know that this will be done automatically. So here, by definition of this, you know that, right? So for example, and this is like this will be constructed by the framework automatically, right? So here are the batch that you feed to the network, and you need to, here you had log, so you need to have gradient of the log, you need to have gradient of the softmax, right? You need to do some transposition of the matrix in order to calculate this. But basically, this part will be done automatically by the framework. And then for the update rule, obviously you need to have the learning rate, and basically this was the update rule. Basically, you're familiar with. So once you have this gradient, right, you need to multiply that with the learning rate, and learning rate is one of the parameter that you need to basically assign, and the previous weight. Okay, so basically this was the previous weight. You need to subtract it and assign it to the new weight. Okay, so this is easy. Do you have any question about this? So I think this is very much straightforward, and is basically somehow a step-by-step construction of this computation graph, how it looks like, not at the conceptual level as we discussed last time, but how really is done by the framework automatically. And like all of the stuff for up until here was the declarative part of the code. And again, back to the code, you see here, like all of the stuff here are just declaration, right? That you declare how you want to compute the stuff, and this should be familiar, at least in terms of what you know. Those of you who are CS level, right? But for those who are not, basically, we have some terminology. It's called lazy evaluation. Basically, you can evaluate things once it is needed. Mostly you declare stuff, and here, like the session run would be only part of the code that really runs, right? So all of the stuff was only declaration, and we we saw that how the code would translate into computation graph. And once you hit this session run, you can basically run part of the computation graph that you need and is used here, right? You can really run even part of this computation graph, right? So you can, in your code, you can declare a large computation graph, but when it comes to running, you can run even part of it. Okay, this is the way how lazy evaluation works, right? So you could declare large stuff, and only when it's needed, you run only part of the stuff that you really need at that time, right? You may need to touch another part of the computation graph later on, right? But every time that you need part of the graph, you can run it right away. Again. Okay, we discussed about the key idea, right? What is the benefit of having this computation graph, right? At least one benefit that we saw last time was this back propagation, calculating of the gradient. So it was easy to see, right? We saw that like for NumPy situation, we needed to do a lot of calculation, a lot of math to at least get the idea of how really we need to do this calculation of the gradient, and we need to write code for that. But with TensorFlow, it is done automatically, right? But there are some system level also ideas, right? We also had the example where you saw very clean-cut example where there might be some optimization opportunities in terms of parallel execution of the code, right? So here, like you saw that, like in this case, we needed to calculate this gradient, right, manually. You saw that like there was a lot of math behind even this line of code, but here it's done automatically, right here. Sorry. So before we go into some system level stuff, for some other languages like PyTorch is also the same computation, the same concepts, very similar. Maybe some implementation, some details might be different. The kind of API that different framework provide might look different, named differently, may run differently, but at conceptual level is really the same, right? So for example, in PyTorch here, you have some very simple few lines of code. You have A, you define it as a variable with a specific size here, right? And you have some other parameters, right? Here, for example, requires grad, it's assigned to true. And then you calculate another variable based on A. So you see the dependencies here with the code, and like when you construct, like you start with A as a variable, then you see B depends on A, right? So you have that. And then like with A, you can calculate B, you can interpret it that way. And then you can calculate C based on B. And then this branches out to two different variables, right? This E and D. So in general, like if you want to, again, make a sense out of it, this was again a DAG. Okay, so the computation graph is a DAG. It starts from somewhere, so you have some leaf. So these leaf nodes are the stuff that will be calculated, will be derived based on the input variables, right? So in the example we had was loss, right? Here is D and E, two computed variables in this case, where for example here in the case of D is a mean of the stuff that you put in C, and the E is sum, right? Two different operations that would result to two different placeholders, D and E. So you see, you get an idea, right, where the DAG should start and where it's end in the neural network. Again, it was these xi's, right? So x1, x2, xn, right? And we had w1, w2, m, whatever, right? And we had this bias term. So we had all of this, and then we had like the stuff, and then at the end we had loss. Okay, so like this node at the end was loss, and this is stuff that DAG started with these input like could be an image, could be text, and this weights was the stuff that was changing. We wanted to learn. Okay, so and make this distinction about don't confuse or don't conflate that like these computation graph are really only for in this scenario taking gradient. Obviously this is the most used one, but you can do arbitrary tricks, right? So you can define a computation graph for something else, for just doing some calculation, not necessarily even touching gradient. Okay, so it is similar in other other frameworks like PyTorch, and others are also the same. But again, for example, like detail required grad here is the case where, for example, PyTorch has the capability if you, for example, calculate D, like do a backward on this graph, right, for calculating D, for example, like if you do, for example, D backward, it start from here, do the computation until it gives you the, it computed that, right? But once this is called, after this was calculated, so basically the these stuff, the values on over these stuff, this variable will be removed because you are done with calculation, and this is a implementation detail in PyTorch where these values are removed to save memory, right? Because we computed D, okay? We computed D, so all the values and specifically the values for A will be removed. So then if you call E backward, it gives you an error. So if you don't set this to true, so for example, if you set this to false, right? But if you set this to true, then you're fine. This kind of implementation detail the type of parameters, the type of optimization. For example, in this case, like whenever like you do this backward, it would remove the values. Might be different, right, for other frameworks, but you got the idea that the whole benefits or the key concept behind computation graph would be the same. Okay, for system, again, we discussed about this is very similar to the fundamental optimization we have had before, even machine learning, right? So for compiler, for example, if you took compiler course, you're familiar with the type of optimization we have for non-machine learning systems, right? Normal software, like dead code elimination. Like if you write code, dead code, you might have some dead code, meaning that like when you run your code, part of your code never get executed in any condition, right? But how you find out about that? Compiler has some optimization for that. Okay, so when translate that to a binary, it identified what part of the code never get executed. So for creating the binary, considers that, because to save memory and to do more efficient computation. And also beyond like some of these optimization, in terms of execution time, whatever, you can think about like memory planning as well. So when you have these computation graph, I mean, this is simple, but imagine that you have a computation, very large computation graph, okay? And you want to deploy it somewhere. Like for example, you want to deploy it on a server, but even doesn't fit there, or you want to deploy it in a multi-device, right? So for example, you want to deploy part of the in cloud specifically, part of the computation graph in one node, another part in some other nodes, right? Or even each node on different server. How you want to do this assignment, right? It's called placement. How you want to place these operations on computational node, or even like for one machine, it has different cores, right? How you want to exploit the fact of parallelization to assigning these into parallel into different cores in order to accelerate the computation. And with graph, it is many of these optimizations are possible. So for example, here you have very simple calculation, right? MXNet again is yet another of these frameworks. So you have A here, you declare A as a variable here, and then you calculate B and C here, and then based on B and C, you derive D. Okay. So in this case, you obviously see that this part and this part can be run in parallel. Okay. Maybe it's not that obvious here. I mean, for this few lines of code is obvious, okay? But like in thousands lines of code, it's not really. But if you translate that to a graph, then you can see these optimization possibilities very easily, or at least graph algorithms, graph optimization can detect that very easily. That's a connection, right? So the parallelization, also multiple devices or threads are the kind of optimization possibility that we'll discuss later in detail how they look like, or at least touch some of those, because like this is yet another research direction, right? So for example, several people and this is very practical line of research, very relevant to companies like Google, Facebook, that runs Netflix, for example, runs thousands of models. So these optimizations, you see that like it's obvious the benefit could save billions of dollars for these companies in terms of cost. And it would boil down to the cost of computation. You know that like for any model, you need to train it, you need to update it. We discussed about all of these. This is not free. Large model is costly to train, also to update, also to do inference. Typically, they are deployed on data centers, and they need to pay for the electricity bill. That's the end of the story, right? So the optimization would provide benefit to basically cost less for all of these operations. And really, in terms of billions of dollars, right? So very practical line of research, exciting, also beneficial. So this is also another, beside this parallel execution, there are much more opportunities. For example, graph simplification, right? The previous one was the case that, I mean, this is the most simplified version of the graph, right? We cannot make it as simpler as this for this code. But there are opportunities for making some other code simpler if we can translate that into something like graph in order to even, for example, remove some lines of code through this graph simplification. Okay, and again, this is a very simple example. We'll discuss about some of these later on in much more detail. And there are algorithms even for, you know, that in graph theory for graph simplification. This is where the actual things will happen. The other opportunities in terms of layout optimization, meaning that like this is a neural network, the architecture of a neural network, which is defined here. Right, so this is where this is somehow different layers of your neural architecture. As you see, very complex. Maybe in terms of layout, you could do better, right? And this is stuff. There are some formats, right? So see different change of format. Like n here is the number of samples that you feed. H is the height of your input. So like W is your width, and C is the number of channel. Right, this is the size of your input, right? So, for example, in the case of images, you have this, right? So each image has a height, a width, and also the number of channels, depending on the type of image, right? So this is another format where you want to construct this tensor by starting from number of samples, then channels, then height and width, right? So this is the conversion that is happening. But really the bare bone structure without any conversion looks like this, right? So you have some ReLU, max pool, reshaping, and then you have this max pool grad and ReLU grad, then identity bias add grad, right? This is a simple computation graph, right? And then, like for example, then you can expand this simple graph by inserting these conversion pairs, right? These conversion pairs are like from this format to another format, right? Different types. Once you insert that, and then you can collapse it to basically make the layout automatically through this very simple algorithm a lot simpler, right? To looks like these instead, right? The same semantically, but this looks a lot simpler by doing this optimization over this graph, right? And this is yet another optimization about graph. And there are, in this ecosystem of frameworks, there are there are different tool support for that, right? So for example, Grappler is one of those tools which basically do these optimizations over graphs, right? So here you see that this is the computation graph. You can connect with this, so you can write with Python, Swift, Java, C++, right? And then you have some other environments, right? So this is embedded environment where you need to use TensorFlow Lite to basically deploy your computation graph on mobile. So you have some tool down the line, or for example, TensorFlow.js in order to do it for web, TF runtime executor, basically for running the stuff on GPU, CPU, right? So you have some so you can think about it that you have some languages that you can write code. This would be translated into graph, and this graph would be needed in order to either run or deploy some different environments. And you can, before doing that, you can optimize this graph using some tools, right? To do these down the line task deployment stuff a lot more efficiently, and especially this is useful for this kind of embedded environments. This is where the real benefit would show up. Okay, that was, so I hope that was somehow a rough, high-level overview of system level in this system stack, right? Again, to recap, we started with this programming level, right? And then here was computation graph, and then here what we just discussed about, like some opportunities optimizing the graph itself, and for runtime prioritization stuff. And then the next, the deepest part of this stack would be related, obviously, to hardware. Okay, so you need some kernel stuff. You need some accelerator in order to connect this with the real hardware, because also, like for example, GPU. Okay, and typically machine learning models are, you know, that at least for training is you need GPU. Basically, you need to run your computation graph, doing all of these optimization, and at the end run it with with GPU, right? So you saw here, we run it on GPU, but obviously there are some other environments, right? So for example, you can run it on very heterogeneous kind of hardware. These are GPU, even CPU, right? This is a small device, mobile, some FPGA, right? You can also run on FPGA stuff, TPU, right? Heterogeneous hardware backend, okay? As you know, as we move forward, more and more of these hardware platforms appear. So we need a layer for taking care of that. So basically you need some libraries, for example, for ARM, right? Running this on ARM. You need some library for TPU, okay? You need some library for CPU, MKL is, for example, for Intel, right? Is a math library doing a lot of nice mathematical optimization at the graph level also when you want to run it on Intel CPUs, and also CUDA library for doing the parallelization. But this was like the era slightly several years ago, right? So that was a kind of a stack that I started. Actually, I mean, before all of these story, right? If you want to think, previously was like the whole stack was somebody needed to, if someone wanted to train a model, needed to do the whole stuff themselves, right? So they needed to write code, for example, in C++, and figure out, okay, how to optimize this code to run on something like GPU, right? Before even having these nice libraries. Like several years ago, there was no TensorFlow or there was no PyTorch. And like it started, the story behind these machine learning frameworks started when people needed to do these themselves. Like if somebody needed to do, like with C, needed to write totally different code in order to run this on GPU, right? If they needed to use Python, right? Totally different story, right? It was a lot of effort for anyone who wants to do machine learning, and that was one of the reasons that why it was machine learning, AI was not moving as fast as we currently moving, right? Crazy, because we have this library that facilitates the stuff. So previously, it probably took like 2 years for somebody to write the whole stack kind of for themselves. And this stack was not really usable for somebody else wanted to write Python. And even at the time was not common to even share code, let alone. So it was a lot of effort. And then these framework appeared slowly by taking care of some of these stuff. And then like some of these optimization, and like it was several years like this where for each hardware people needed to deal with this detail of, like, for example, I want to run on Intel, right? I need to deal with this MKL library. But then like from a few years ago, people started looking at maybe we need another layer here, okay, to take care of translation from system to some low-level stuff that could be reused across all of these hardware platforms. And that was the area where people look at these compiler. So compiler-based approach. And there are some nice compilers out there for specifically taking care of this hardware layer. there are opportunities, like again, several optimization at this layer, and this make it reusable for when a new hardware appear, right? Still can people do this, right? At least with some extension in these layers. So the extension would go into this layer, and you don't need to deal with each of them separately with different libraries. So it is more clear cut and more integrated with like these upper layer. So some of these parameters that you need is here, you can like declare stuff, declare it in, use it in, change it in the programming level, right? If needed, right? Or abstract it away if not needed. Okay, do you have a question about this? So the plan, so now we got an idea, okay, how the whole stack of machine learning stack look like. We now know why at least we need this stack. What are the opportunities it provides, and some details, but I would like us to go into some more detail about specifically some of this optimization we can do at the graph level, and also for parallel execution, because like these are important aspects of this framework, and it provides you some insight, and the key beauty of it is again that these insights are reusable across different environments, right? These are very useful for you when it comes to constructing or building a machine learning system, right? These are very important skills for you guys to learn. Actually, these are the skills that companies like Google, Facebook are highly needed, right? Talking with these folks at Google, for example, or other companies like NVIDIA, they're really in need of folks who are familiar with this concept, not necessary for a specific framework, but have an intuition about the opportunity and have the skills in order to extend these frameworks. You know that like Google is the main company behind TensorFlow. Obviously, it's an open source ecosystem, but Google is driving that framework, and Facebook is driving PyTorch, for example. So these companies need these skills, and this is really exciting and important. That's why I would emphasize that this course is really important for you guys to learn some deep concepts about machine learning system, and hopefully this would give you the skills that you require if interested. One path for you could be, some of you may be interested going to industry afterward, right? Even for those who are interested to do grad level research, we are discussing research opportunities throughout this course, and there are numerous opportunities. Even it's enough to only like focus on this layer for decade. There are numerous challenges in even one of these layers across the stack to do research. So it would be exciting. So I would wait a few minutes here if you have questions, please. Otherwise, we stop. Thank you, guys. So
Thank you.
see you next week. No, not next week, on Thursday.